All right, next we will have Jiang. She's a PhD candidate in medical physics at the University of California, San Francisco. Her research focuses on the application of deep learning in radiation oncology, specifically in automated treatment planning and dose prediction. And she's currently working on developing and validating clinical workflows that integrate AI models with commercial treatment planning systems to enhance efficiency and plan quality. This is very interesting. Welcome, Lou.
Okay, thank you so much for the introduction. Hello, everyone. Good morning. My name is Lou. I come from UCSF. So today, I want to give you some our project updates about integrating deep learning with RayStation dose mimicking function for automated treatment planning. And so my co-authors and mentors, Dr. Kishan and Dr. Min Song, reports funding and consulting fees, and other authors in this project have no conflicts of interest. For this short presentation, so I want to describe the workflow mechanism of integrating deep learning-based dose prediction, which is relatively really popular topic in the research area, and also with the RayStation dose mimicking function. And I'll also talk about how to evaluate the quality of the automated VMAT plans compared to current gold standard manual clinical plans. That's very interesting topic recently. And finally, I want to identify the efficiency gains and one-click workflow improvements that can be used in a clinical setting. So for the research motivation, for a lot of AI models, I think the biggest challenge is the data scarcity. So if we want to have a high-performance AI models, we need massive data. Let's say over 1,000 plans, or maybe 10,000 plans. If you look at current LLM models, the data is even larger than this. But however, for small clinics and for rare sites, for example, pancreas patients, we don't have that sufficient data to have a really good, robust AI model. So my strategy in this topic is I train a foundation model, so which I use, I train the model once and adapt the model everywhere. We have public data sets, which we call public priors, and we apply this knowledge in the public data set to our local minimum data set, which we can use probably less than 10 patients to get a relatively robust AI model. And the final solution, I use the RayStation to integrate the plan. The prediction is really good. It's really ideal. It's really theoretical, but it's not a plan. So I want to use this dose mimicking function to make the plan deliverable under 15 minutes. This is my current time for the automated planning. For the workflow, the first stage is pre-training. Actually, this is AAPM Grand Challenge dataset, which is about more than probably about 3,200 patients, including head and neck, and also the liver cases. So for the pre-training stage, the public dataset has the, actually it's not clinical plans. They use their batch script generation, so they create over 1,000 plans using the TPS system, but it's not clinical ground truth plan. And the second stage, I use the transfer learning strategy. So I pre-train the model, the foundation model, on the larger cohort set in the stage 1, and then fine-tune the model on the specific site, which is head and neck data set and the pancreas SBRT plans. So this strategy allows the model to adapt our specific institution protocols without needing a huge local data set. As you can see, the pancreas cohort is really limited. So the step 3 is very important. Predicted dose is just a picture that I just said. It's not a treatment. We feed the AI dose into the RayStation mimicking optimization engine. So it's like a fallback planning. This converts a pixel data into the machine parameters, like generating VMAT plans or any kind of plans that we want. For the evaluation stage, it's actually divided by 2. The first, we want to evaluate the predicted dose with the clinical ground truth dose. And for the second stage, we want to evaluate the plan quality. So we compare the converted plans with the clinical plans. And then I want to talk about the efficiency and robustness in this study. So for the model configuration, if anyone does not not familiar with those prediction, so for the AI model, we put planning CT and structure sets into the model, which is PTV and OAR mask. And for the output, which is label, because it's supervised learning, we use a 3D voxel-wise dose prediction as the 3D voxel-wise dose distribution as the output. And for the strategy, I initialized with a foundation model weights instead of random model to start with. And then for the performance gains, I really want to emphasize the 3 points here. The first is data efficiency. You can see from the figure that I show on the right here, it's a very standard UNet AI model. So if we train the model from scratch, we probably need about 50% of training data set, which is about 100 patients or 200 patients in our cohort. But however, if you use a fine-tuning strategy, transfer learning strategy, we only need 5% or even less. It's about 10 cases. So you can see the data efficiency. We don't need a lot of data, but we can relatively get a good model with the transfer learning strategy. And you can see a lot of spikes over here. So if we train an AI model with limited data, for example, 5% or 10% or 20%, the AI model is probably getting overfitted or we don't know where it goes. So the arrow can be the spikes can be really frustrating. But if we use a fine-tuning strategy, we use a foundation model as the regularization at the initial stage. The model robustness can be really good. We can see the lines, the yellow lines here, so it doesn't have any spikes at all, maybe a little bit. So I think the second performance I want to see is the convergence speed. If you train a model from scratch, the model can take about 200 or 500 epochs to converge depending on your data set. However, if you use fine-tuning strategy, which is also transfer learning strategy, you probably only need 10 epochs or 20 epochs, which is about 20 times faster than training the model from scratch. And the third thing, I just say it's you use a fine-tuning strategy. It can maintain stable and high accuracy in extreme low data situations. And this is clinical integration that I just finished. But I probably will improve it just using all the things in the RayStation. So right now, I made a Java extension tool to integrate Mim with containerized AI engine. So it is a platform-independent development because it's a Docker container. So you can run it in your any kind of laptop, Windows, MacBook, or Linux system. So when you open the Mim and you click the launch extension, it will automatically predict the dose and send the RT dose file back to Mim. And once you review it in the step 3, if you okay or happy with the dose, so you can push it to the RayStation, and we can use a mimic dose on the step 4 to convert it to any kind of treatment plans. So for the efficiency, the AI dose prediction, when we talk about the AI model prediction, it only needs 1 second if you use GPU. But if you use your CPU or use your OM MacBook, it probably take 1 minute. And the usability is really efficient. It's just one-click solution. Just choose extension. And then, so this is the RayStation integration details. So I want to make everything pretty standard. So I use the VMAP plans that currently popular in the clinic. So I use full arcs with 6 MV photons for conventionally fractionated head and neck cancer, and 2 full arcs with 10 MV photons for pancreas and CBRT plans. These 2 templates can be adjusted based on clinical protocols. And for the dose mimicking in RayStation, I just use a default setting, target with OER weight ratio 100, and voxel dose priority 0.1. However, these two hyperparameters can be adjusted, and I believe it can be further fine-tuned to get a better plan. And this is the screenshot that I made in our RayStation software. I believe it's 2024 version RayStation. And on the right side, it's the template plan that I create. I named AI version 2. And on the right side, on the left side is empty plan. Is that like the ideal dose prediction from the AI model? And on the right side, which I call a template plan, is AI version 2. It's the plan that convert the predicted dose into actual plans. So you can see from like the image here, the DVH figure actually match very, very closely. So I think the RayStation have really good function. The dose mimicking can really replicate the predicted dose in your plan. And then this is clinical validation. I further take a look at each specific and pick some interesting cases. So first, look at the DVH comparison on the left. The solid lines are the AI-generated plans. The dotted plans are predicted dose. And the dashed plan, which I call clinical, is the clinical ground truth plan. So as you can see, the curves overlap most perfectly, demonstrating that AI learned to prioritize their target coverage, especially the PTV high, which is about 70 gray. But however, you can see the difference in the PTV low region and also the PTV medium region. There's a shoulder, which is the clinical plan. But however, if you compare the organs at risk, you can see the AI model, the AI plan is actually achieving a little bit better compared to clinical plans. So we also verify the AI plans using the Mobius 3D PSQA, is currently our institution protocol, and the dose difference consistently less than 1%, so which is really good. So the entire process is less than 15 minutes, but I believe it can be further accelerated if we use a better GPU or better computer. And then this is a more interesting case. So this is the pancreas SBRT plans. So as you can see, the AI model, which is solid line here, achieved a reasonable agreement with clinical ground truths, effectively handling the sharp dose fall-off on the DVH figure I show you here. So the homogeneity index in PTV is better in the AI plan. However, this case is really tricky because in a lot of pancreas patients, physicians and dosimetrists don't really prioritize the homogeneity in PTV. But the AI model is a regularization, so it kind of like try to enforce the model to make the PTV look really homogeneous. So I don't know what's the next step to make the AI model aware of that. We don't need a lot of like dose, or we don't need a lot of sparing here, but I'm trying to work on that. So consistent with the head and neck results, we maintain the Mobius difference, like the patient-specific QA less than 1%. And the AI planning time is less than 10 minutes. I guess because pancreas case, we have less OERs involved, so that's why the planning time is reduced a lot. And this is deliverable verification. It's patient-specific QA. So yeah, the agreement is very consistent. So I can say dose mimicking generates valid physically machine parameters. And the clinical takeaway here is like the clinical review is really, really important because AI plan sometimes does not perform well in the PTV and some really close OERs. And I want to give a closer look on the PTV, on the DVH here. So we can see from GTV and ITV, actually AI plan, the solid line here is really good. But when we look at the PTV, the coverage is not really satisfying. I make some arrows over here. I think it's because the AI model is trying to avoid the large bowl and bowl small, so that's why the coverage is not enough. So then for the summary and conclusion, yeah, it is a very efficient and user-friendly workflow that I propose. It is a one-click workflow. It's very easy to use in MIM and RayStation, and it can save a lot of time, generate deliverable plans. And the foundation model has transfer learning strategies, very data efficiency, and we only require like minimum local data. And I will make every like the extension or the Docker and also all the code open to public. And after the review is done, I will just put everything in the Hugging Face and GitHub. And also the third part, clinical review is essential because I just show there are some disadvantages in the AI plan, how like we really need to care about the PTV coverage and how we balance the trade-offs. So AI is just an assistant. It provides high quality starting point, but the physician's dosimetrist review is very important. And for complex situations, we need to carefully adjust the plan and achieve patient-specific goals. And then, yeah, I just want to thank for my supervisor, Dr. Kishan, and my co-author, Dr. Hirata and Dr. Potter is here, and Dr. Mings and Dr. Cao, and the whole entire lab at UCSF. And also, I want to give special thanks to RaySearch Laboratories. Thank you so much.
Thank you, Dr. Jiang. Any questions?
So this is like another tool, right? And like sometimes you need a hammer, and sometimes you need a screwdriver.
Yep.
Like in terms of like implementation into a clinic, like long term, how do you see this playing out? Do you see what scenarios do you see this sort of like approach being most useful for? Because obviously you probably won't be able to use it for everything, and it won't be practical for everything, right?
Thank you for the question. I'm not a doctor yet, but I will be becoming one. So like I remember there's some really interesting research that has published about prostate treatment planning automated. And I think they're already made some softwares or extension tools that can make the prostate treatment planning very efficient and with no human efforts. And I believe, so I believe the AI will be a really good tool in the probably next few years. But the AI model is really a prediction or a regularizer. So I think it will be a really good starting point and save some time, but it cannot replace any manual work to review the plan. So, and I believe for a relatively simple case, prostate or bladder case, it can be fully automated. But for really difficult case, pancreas and head and neck case, I don't think it can be a really good, like, as compared to physicians or dosimetrists.
Thank you for a nice presentation. I just wanted to mention so that everybody knows that RayStation also has a built-in feature that does pretty much exactly this, using deep learning to predict those distributions and then mimicking to provide the deliverable plan. Again, there's a differential between what's available here compared to what's available in Europe because of the regulatory constraints that we've discussed before. But in the latest version that's available in Europe, we have a lot of different clinical sites where we employ a method that's similar to this. One difference that I would like to point out also, maybe as an advice to you, I noticed you use the fallback planning function to do the mimicking. That's actually designed for something else.
Yes, I
where
know that.
we suppose that there may be a change in beam arrangement or treatment technique. So that's why we have such a low default weight on the voxel, prioritizing the voxel dose. So depending on how clever your prediction is in understanding what the impact of the beam arrangement is, you could increase that factor. So if you predict VMAT, like coplanar VMAT-ish distributions, and you mimic it with coplanar VMAT, then you could go really high.
Yeah.
But here you venture into the more complicated territory of having those predictions that are aware of the treatment technique. Because for non-coplanar, if it's a wave arc, then you should predict differently, or for protons. So that's kind of the area where we have been working.
Yeah, thank you so much. Yeah, I know RayStation has like their own automated treatment planning, and I know it's really good. So I think my work is I try to see if we can implement various AI models. So because my work does not only include UNet, I also use diffusion and transformer and any kind of like efficient plans. So yeah, I try to use more AI models to compare. Thank you.
And Dr. Jiang, last question. Do you, how much of this is used clinically right now? How are you using these dose distributions and then having the planners work on it and actually deliver clinical plans?
It is not used in the clinic yet, and I don't know where. I don't know when we probably can trust it. Like,
well, the dose is the dose, and the plans are the plans, right? I mean,
Yes.
they still have to be reviewed, like you said. So,
Yes.
just curious.
So right now, I'm just like fine-tune the plan to see if I can achieve or beat the clinical plan. So right now, the current stage is comparable. So, like, yeah, I hope I can implement that in clinical workflow. So right now, the workflow is set up. Just need to be really cautious about it.
Very good. Thank you.
Thank you.
Thank you.